In this chapter, we're going to look at electronic structure as well as periodic properties of elements. And what we're going to do essentially first is look at light. So we're going to talk about some general information about light and including some of the physics equations that govern some of the properties of light and things like that. And then after we look at light, we're going to look at where light comes from, and that has a lot to do with the electronic structure of an atom. Then finally in this chapter, we're going to look at some of the periodic properties of the periodic table, or some trends on the periodic table is another way of putting that. So let's get started with some of the nature of light. So here you could see some image of some distant stellar group of objects, stars, here in this picture. And that light is traveling all the way from those stars to here. So you may have wondered, well, where does light come from? And we're going to start with, as I said, talking about light. But then in a little bit, we're going to start to look at, where light comes from and how light works. So the first thing we need to realize about light is that it's electromagnetic radiation. So it has two properties. It has an electric field component, which is written here as the darker line, and a magnetic field component, which is here as the kind of blurry line, if you will. So it has these two components. And these components have different properties. One of the properties is the wavelength. So the wavelength, which is given by the symbol lambda, is the distance from one crest of the wave to one crest of the wave, or one trough of a wave to one trough of a wave. So you'll notice here that this light has a relatively long wavelength, this has a shorter wavelength, and this has a shorter still wavelength. Well, it turns out that the speed of light is a constant. In a vacuum, it's about 3 times 10 to the 8 meters per second. So there's this other property of light called the frequency. The frequency is, if you were standing on this line, for example, as an observer, how often would you see a crest? So if you look here in 1 second, you would see 1, 2, 3, 4 crests. Here with a shorter wavelength, you would see 8 crests. And with a shorter still wavelength, you would see 16 crests if you were standing here for 1 second. So this is called the frequency of light, and it's in hertz, reciprocal seconds, which is how often the light passes a given point, how often a crest of the wave passes a given point. So this has a long wavelength and a low frequency. This has a short wavelength and therefore a high frequency. The reason that wavelength and frequency are related is because the speed of light is constant. So therefore, since the speed of light is constant, if you know the wavelength, you can also calculate the frequency. And when I say they're related, I mean if you know one, you can calculate the other. So that's basically what's going on with frequency and wavelength. There's another property of light which is called amplitude. So the amplitude of the light is kind of the intensity of the light. So when certain electromagnetic radiation has a certain wavelength or a certain frequency, which they're related to each other as we just discussed, it will have certain properties. So for example, red light has a wavelength of approximately, 680 nanometers. So that light will be red. If the wavelength of this light was 680 nanometers, this would be red light and this would be red light, because the wavelength or the frequency determines the type of electromagnetic radiation. In this case, my example, red light. The amplitude, the distance between the crest and the trough here, or the amplitude of the light, is going to determine the intensity. So this would be a dim red light, for example, and this would be a bright red light. And I should mention, I said that the amplitude is the distance between the crest and the trough, but it's actually the distance between the midpoint and the crest. So this here is the amplitude. I misstated that a second ago, and on this case, this is the amplitude. But in both cases, or either way you look at it, correctly looking at it, it's from the midpoint to the crest. This is the amplitude of the wave and is the intensity of light. So this is a bright red light and this is a dim red light if the wavelength is appropriate for red light. So there are three fundamental units of light, or measures of light, that you need to be familiar with. And they are wavelength, frequency, and energy. And for energy, we're skipping ahead a little bit because this equation comes a little bit later. However, it's really important to remember that the wavelength, the frequency, and the energy are all properties of light, and they're all related by constants. Said another way, if you know the wavelength of light, you can calculate its frequency and its energy. If you know the energy of light, you can calculate its frequency and wavelength. If you know the frequency, you can calculate the wavelength and the energy. Again, they're all related by constants. So wavelength and frequency are related by the constant, the speed of light, 3 times 10 to the 8 meters per second. You could see this in other books as 2.998, but just to make it a little easier to remember, I used just 3 times 10 to the 8 meters per second, and I gave it the 2 zeros. Said another way, this is 3 significant figures as opposed to 4. The lambda is the wavelength, and it has to be in meters because the speed of light is in meters per second. And nu is the frequency, and it's in hertz, or reciprocal seconds per second. And as we discussed before, since the speed of light is a constant, if the wavelength is long, the frequency is low. If the wavelength is short, the frequency is high, because more crests will cross your path if you have a shorter wavelength. One other thing that often comes up when it comes to wavelengths is the wavelength is often given in nanometers. A nanometer is 1/1 billionth of a meter, or said another way, the way I remember it, 1 billion, or 1 times 10 to the 9 nanometers equals 1 meter. And this equality will come up, and we're going to do a couple examples in a couple minutes. So wavelength and frequency are related by the speed of light. I do want to point out one more time, this is not a V. V is velocity. This is a nu, so this is frequency. Wavelength and energy. Wavelength and energy are also related. E equals hc over lambda. H is also a constant. It's called Planck's constant, and it's 6.626 times 10 to the minus 34 joule seconds. 6.626 times 10 to the minus 34 joule seconds. C is still the speed of light, 3 times 10 to the 8 meters per second, and lambda is still the wavelength in meters. So if we know something about the wavelength, we know something about the energy. Note that energy here is on the top, if you will, it's over 1, and wavelength is on the bottom. This means that these things are inversely proportional. So if the wavelength is long, the energy is low. If the wavelength is short, the energy is high. That is very important to remember. And we can combine these two equations. So said another way, we could solve this one for lambda and plug it in, and we get E equals h nu. So if we had the frequency and the energy, they're related by Planck's constant. So these are 3 fundamental equations that we need to be familiar with in this course. And the other thing that I want to just let you know about is that if we look at electromagnetic radiation, and for example, it is high energy, and we use the equations that we just looked at, E equals h nu, and E, whoops, those are off the screen, E equals hc over lambda. If you look at these equations, energy and frequency are directly proportional to each other. So if energy is high, it must also be a high frequency. And if energy is high, as we talked about a minute ago, the wavelength must be low because it's on the bottom, so they're inversely proportional. So it must be what is called short, because it's a distance, wavelength. Instead of low wavelength, we call it short because it's a distance. On the other side of the scale, if we have low energy, we must also have low frequency and long, instead of high, wavelength. So this is basically how it works. So if we know something about the relative energy, we also know something about the relative frequency and the relative wavelength. We can actually mathematically calculate the other 2 of these things if we know any one of them. And that fundamental principle is extremely important. So what I would like to do now is look at a few examples where we actually do these calculations. So it says calculate the wavelength of red light in nanometers emitted by a neon sign with a frequency of 4.74 times 10 to the 14 hertz. So if we use the equation C equals lambda nu, well, we want to rearrange because we're trying to solve for lambda. So we divide by nu, and we get lambda equals C over nu. Now we can plug in the speed of light is a constant, 3.00 times 10 to the 8th meters per second. The frequency is given 4.74 times 10 to the 14 hertz. A hertz is per second. So it's how often something happens in a second. How many times a crest passes an observer in 1 second. When we do this division, we get to 3 significant figures, 6.33 times 10 to the minus 7 meters. So 6.33 times 10 to the minus 7 meters is the wavelength of this electromagnetic radiation. However, it asks us for the wavelength in nanometers. And the reason that nanometers come up so often is because hundreds of nanometers are visible light. If we look at visible light that's around 400 nanometers, it's kind of a purple, indigo, violet type color in that area. And then if we look at it around a little bit less than 700 nanometers, it's red light, and it's everywhere in between, and it's all the continuous electromagnetic spectrum, which is if you take the light and break it up into a rainbow. But anyway, those are hundreds of nanometers. So at the end of the day, we want to convert this to nanometers. So if we start with 6.33 times 10 to the minus 7 meters times, well, 1 meter is 1 billion nanometers. So we put 1 meter on the bottom and 1 times 10 to the 9, or 1 billion nanometers on the top. Multiply by the top, divide by the bottom, and what you find out is that this light is 633 nanometers. All right, so that might be red or an orangish color, somewhere in that region. Again, it's a continuous electromagnetic spectrum, so it can be difficult to tell sometimes exactly what's red. There are different shades of red, for example. Anyway, that's not the point here. So this is how we can calculate the wavelength of light based on its frequency, because it's related by a constant. Well, here we're asked to do the opposite. Calculate the frequency of green light emitted by a hydrogen atom with a wavelength of 486.1 nanometers. Well, we need the same exact equation. C equals lambda nu, except this time we're solving for nu, so we want to divide by lambda. Nu equals C over lambda. However, the wavelength is given in nanometers. In order to plug into this, we need a wavelength in meters. So we start with 486.1, whoops, I put those backwards. Let me try again. 486.1 nanometers times, this time we want the 1 times 10 to the 9, or the 1 billion nanometers on the bottom to cancel out, and the 1 meter on the top. And what you find is it's 4.861 times 10 to the minus 7 meters. If you notice, a number in scientific notation times 10 to the minus 7 meters is hundreds of nanometers. It's here as well. And that's just a thing that happens with this math. Now, we need to take these number of meters and plug them in. So we use 3 times 10 to the 8th meters per second, the speed of light in a vacuum, divided by the 4.861 times 10 to the minus 7 meters. And when you do that math, you find out that the frequency is, just 3 significant figures, 6.17 times 10 to the 14 hertz. So now we figured out how to convert from frequency to wavelength and wavelength to frequency. So these are just the opposite conversions. What's important to remember is if I know the wavelength or I know the frequency, I can calculate the other one. In the next examples, we actually want to look at the energy conversions. So in this case, we're given a wavelength and we want energy. We could also be given a frequency and find energy using the other equation. So here we have E equals hc over lambda as the equation. And it says, calculate the energy of violet light emitted by a hydrogen atom with a wavelength of 410.1 nanometers. So here we want to use E equals hc over lambda. Well, this is E equals Planck's constant, h, 6.626 times 10 to the minus 34 joule seconds, times c, 3 times 10 to the 8th meters per second. These are both constants. Divided by the wavelength. There's a problem though. The problem is that this wavelength is given in nanometers. We need to divide this by 1 times 10 to the 9, 1 billion, to find how many meters it is. And if you remember from the previous example, it's just 4.101 times 10 to the minus 7 meters. Hundreds of nanometers are times 10 to the minus 7 meters. To check this, you just simply divide it by 1 times 10 to the 9, or you multiply it by 1 meter over 1 times 10 to the 9 nanometers, and you will get this number. Now that I've plugged in, I find that the energy is 4.85 times 10 to the minus 19 joules. And this is really, really important, because what we need to realize is this energy is really, really small. Just like the mass of an atom is really, really small, the energy of an individual photon is incredibly small. Now, if you think about the fact that the Earth gets most of its energy from light coming from the sun, well, how is that possible? Because light has almost no energy. And the reason that's possible is because we have lots of photons of energy. So when we do E equals hc over lambda and we find the energy, we're finding the energy of a single photon. And that brings us to our next question, where it says how many photons are contained in a burst of yellow light, 589 nanometers, that contains 609 kilojoules of energy. Well, we want to do the same thing. E equals hc over lambda. E equals h, Planck's constant, 6.626, times 10 to the minus 34 joule seconds, times 3 times 10 to the 8th meters per second, divided by the wavelength in nanometers, so divide by a billion, which is 5.89 times 10 to the minus 7 meters. So we have to convert those nanometers to meters before we can plug in. In all of these equations, the wavelength has to be in meters, and that's because the speed of light is meters per second, so we need those meters to cancel out. When you do this, you find that the energy of this photon is 3.37 times 10 to the minus 19 joules. And this equals the energy of one photon. Now, before we can find how many photons we have to notice that this energy is in kilojoules and this energy is in joules. So I either need to convert this to joules or this to kilojoules. For whatever reason, it doesn't really matter which one I do, I'm going to convert this to kilojoules. To do that, I divide by 1,000. So it's 3.37 times 10 to the minus 22, which is this number divided by 1,000, kilojoules equals one photon. Now I can have an equality that I can use to do my dimensional analysis. Starting with 609 kilojoules times, well, I want the kilojoules on the bottom, 3.37 times 10 to the minus 22 kilojoules on the bottom, and one photon on the top. And when I do that math, I find that there are 1.81 times 10 to the 24 photons, which is roughly 3 moles of photons. So in order for light to transfer measurable amounts of energy, there has to be lots of photons. Just like for molecules to provide a considerable amount of mass, such as all the water on the ocean, there has to be lots of water molecules. Okay, so it's a similar idea here. An individual photon has a very small amount of energy, just like an individual atom or electron or proton or whatever has an incredibly small mass. So these are the ways that we can convert these. And I just want to one more time bring it back to the other idea, which I can't seem to find here, that there is a relationship between energy, frequency, and wavelength. If something is high energy, it's high frequency and short wavelength. If it's low energy, it's low frequency and long wavelength. So if I know one variable, I can calculate the other two. The previous 4 problems that we did showed interconverting all of these variables. We did not convert frequency to energy, but that can be done as well. We would just use this equation instead of using this equation where we converted wavelength to energy. Planck's constant is still a constant. So now that we've looked at some of the calculations that we can do using these equations, let's look at the continuous electromagnetic spectrum. And the continuous electromagnetic spectrum is shown here. So you'll see that in this direction we have increasing energy. So over here we have high energy. We have increasing frequency in this direction, so high frequency. And we have increasing wavelength in this direction, so short wavelength. And you can see the wavelengths here are shorter. So over here we have high energy, high frequency, and short wavelength. And over here we have low energy, low frequency, and long wavelength. Now let's look at the continuous electromagnetic spectrum. Here we have gamma rays. Gamma rays are the highest energy, highest frequency, shortest wavelength rays. These are the types of things that are given off in nuclear reactions or in nuclear weapons. These things are extremely dangerous. They're also in cosmic radiation as well. So these are very bad for human health and stuff like that. The next highest energy type of electromagnetic radiation is X-rays. X-rays are used, of course, for X-rays of your skin. They pass through soft tissue, but they do not pass through hard tissue, so someone could see, for example, if there's a break in the bone. X-rays are also a fairly dangerous type of electromagnetic radiation. So if you've ever gotten a tooth X-rayed at the dentist, they put that heavy lead shield over you, or apron kind of thing, and that is to protect you from the X-rays to get them as little as possible. Now, I'm not saying you shouldn't go get an X-ray because it does have its benefits, which is why it's done, but there is a reason that they protect you, and also they don't give people X-rays all day every day because that would be very bad for their health. Ultraviolet rays. You've probably heard of ultraviolet rays that come from the sun. And this is why we wear sunscreen in the summer, to block these ultraviolet rays and keep them from getting on our skin, which can cause tan, but if at the extremes, it can cause things like skin cancer and things like this. So these are ultraviolet rays. Visible light. This is the very small part of the continuous electromagnetic spectrum. However, it is very important to humans because this is what we can detect with our eyes. And you'll notice that visible light is broken up into the continuous colors. So this is your Roy G. Biv, red, orange, yellow, all of these colors in Roy G. Biv. Note that here, when you write it this way, it's backwards. So red is here, so it's kind of Roy G. Biv backwards, and they flipped it around here so you can see the visible light. If you write the electromagnetic spectrum the other way, then the Roy G. Biv is in the correct order. So again, high energy waves, higher in energy than visible light, are your gamma, your X-rays, and your ultraviolet. On the other side, we have energy types of radiations that are lower in energy than ultraviolet light. Infrared, this is heat energy. This is how night vision cameras work. If a person is relatively warm compared to the environment, they'll show up on a infrared camera because they're emitting more infrared radiation. This is also how remote controls work. The next one, I'm going to skip terahertz, is microwaves. So microwaves work on things like a microwave oven, and also things like cell phones and wireless data work on in the range of microwaves. And then finally, we have radio waves, which are your broadcast and your wireless radios, including your AM, FM radios, and stuff like this that are working on these radio waves. It's important to note that this is a continuous spectrum. So X-rays isn't one energy or one wavelength or one frequency, it's a range of wavelengths. Visible light is a range of wavelengths, although it's a very small range of wavelengths. Radio waves are a range of wavelengths, and you can have wavelengths of energy anywhere in between. Now, something that we've alluded to, but haven't explicitly stated here, is the dual nature of electromagnetic radiation. Sometimes we've been talking about it as waves with wavelengths and frequencies. But believe it or not, when we talked about the energy, we were talking about photons or packets of energy, each individual photon containing some energy. So one interesting thing about electromagnetic radiation is it has both particle properties and it has wave properties. So let's just look at a couple of examples of experimental evidence that we have for these two things. And the reason this is important is because although chemistry doesn't really deal with light, it deals with electrons. And electrons also have this dual nature where they have particle properties and they have wave properties. So let's look at this. Waves are able to interfere. So if you add this red wave and this blue wave, so the crests are approximately lined up, the troughs are approximately lined up, and the crests are approximately lined up, so they have the same wavelength, and they're relatively in phase, the amplitude actually doubles. So the resulting wave has the same wavelength, but the amplitude from the midpoint to the crest is doubled by adding these two waves together. Waves can also have destructive interference. So here, the crest of this wave and the trough of this wave approximately line up. Here, crest and trough approximately line up, and here, crest and a trough approximately line up. The resulting wave has a much smaller amplitude. And in fact, if the crest and trough lined up perfectly, the resulting wave would be flat. This is actually how noise-canceling headphones work. In this case, it's sound waves. Basically, they have a microphone in them, and then through the speakers, they try to put the opposite sound of what you hear in the room so that it will destructively interfere and you don't hear the room sounds. So waves can constructively and destructively interfere. Physical things can't do this, right? If you think about a baseball, you can't have constructive and destructive interference of baseballs because baseballs don't really have wave properties. But light does have wave properties, so light can do these things. Another property of light is that it will diffract. So what we're looking at here is kind of a top view of waves. So this is a crest, this is a crest, this is a crest, this is a crest, so on and so forth. These are all crests. If you put light through a slit, it will come out in this circular pattern. So it will not come out straight. And it turns out that if you put light through two slits, you can end up with what is called the diffraction pattern. These bright spots are where these waves overlap such that they're constructively interfering. You get a bright spot. These dark spots are where the waves overlap and you get an interfering, or destructive interference, and you get a dark spot. And you get this pattern of bright spots and dark spots. Notice that if you just put particles through here, if you just shot a particle of baseballs and this was a hole in the wall, you would see a bright spot here and you would see a bright spot here. But if you put light through these double slits, you see this, what is called interference pattern. Regions of constructive interference, destructive interference, constructive interference, destructive interference. And this tells us that light has wave properties, both because of the diffraction and because of the interference. And this is called the diffraction pattern again. So these are a couple of ways in which light is known to have wave properties. Let's look at a way that light is known to have particle properties. And this has to do with something called the photoelectric effect, which Einstein is famous for. So the photoelectric effect is an interesting effect. What we have here is we have two charged plates in a vacuum. So this round circle is indicating that there's a vacuum in here. Vacuum means absence of air. So there's no air in here. And here we have a switch. And we apply a high voltage. So this is a negatively charged plate, and this is a positively charged plate. A negatively charged plate has a bunch of electrons on it, and those electrons are attracted to the positively charged plate. However, normally speaking, we would consider that this circuit is off, and we're measuring it here to see if there's any current flowing or any electrons flowing. The reason it would be off is because this part and this part are separated by space. So if they're separated by space, the current can't flow. Well, it turns out if you turn the lights on and you have this electromagnetic radiation, if the electromagnetic radiation hits the charged plate, it can cause an electron to eject and fly to the other side, and we can measure a current. And this is called the photoelectric effect. This is extremely, extremely important to everyday life because anything that has a light detector in it, such as something potentially that can tell if your refrigerator is open or closed, if it has a light detector in it, it works on the photoelectric effect. So we use this practically in many, many, many different types of devices. As an example, let me show you. If you have a device which has a system that looks like this, where you have a light source here shining in this direction, and here you have a photoelectric detector. They're called photomultipliers, but I'm just going to call it a photoelectric detector. If this photoelectric detector feels an amperage because the light is able to shine through it, then it knows that there's nothing in here. Now when the refrigerator door closes, for example, it's designed so that it puts a small piece of plastic or metal in between here. Now the photoelectric detector, the light is being blocked by the piece of metal, and therefore, metal or plastic, and therefore the refrigerator knows the door is closed. When you pull this back open, it's open. When you push it back closed, it's closed. So this piece can move with it's attached to the door, so that if there's a current detected, it knows it's open. If there's no current detected, it knows it's closed. Now, I'm not saying all refrigerators work like this, but there's many devices that work like this, and there's many other interesting ways in which photoelectric detectors work. For example, basically my room can detect whether the lights are on or off using a photoelectric detector. So here is the photoelectric effect. So you might be wondering, well, what does this have to do with the particle nature of light? And it has a very interesting thing to do with the particle nature of light. So let's look at it a close-up. This is the negatively charged metal plate. And these are wavelengths of light hitting it. If light was a wave, if we were working with the wave properties of light, if we increase the amplitude or we made a brighter light, we should get more electrons ejected. However, it turns out that's not how it works. What matters is the wavelength of light. So, a 700 nanometer light, a red light, is not capable of ejecting electrons. However, a 550 nanometer light will eject electrons and you'll absorb a current. A 400 nanometer light will eject electrons and they'll leave with even more velocity. They'll have more energy when they, more velocity when they leave because this is a higher energy part of light. This means that light is like packets of energy, and those packets of energy are called photons. And Einstein won the Nobel Prize for this work. So this is very important and interesting work. It's not really a focus here. The photoelectric effect is very important, and it works in many of our chemistry instruments, but it's not a main focus here. At the end of the day, what we want you to know is the dual nature of light. Light has wave properties. It has a diffraction pattern. It can interfere constructively and destructively, as well as it will diffract through slits. And then there's the double slit experiment. Light has particle properties, and we know this because of the photoelectric effect. Again, why this is important in chemistry is because electrons can also have particle properties and can have wave properties. And after we discuss where light comes from in the next section, we'll come back to this idea and we'll talk a little bit about the particle and wave properties of electrons.